video, I'm going to do a walkthrough of the normal mapping chapter from the notes. Okay, so on the previous chapter on lighting, we saw that the lighting model used the normal vectors to determine diffuse and specular reflection. So just to explain what normal mapping is, so here we have a surface, and the normal vectors on this surface are all pointing in the same direction. So when we apply a normal map, the geometry of the perceived surface is essentially a straight line, or it just follows the curve of the surface. So what normal mapping does is it maps the normal vectors across the surface. So here we have, if you look at this bottom diagram here, we have normal vectors pointing all sorts of directions, and when we apply the lighting model, the perceived surface is that of a non-flat surface. Okay, well the polygon is actually flat, but to the viewer it perceives it being non-flat. So it's quite an efficient way of getting geometry into our models. Okay, so in this lab we're going to be looking at applying normal mapping to our objects. Okay, now this is what a normal map looks like. It's actually just a texture. So the color of each textile in the texture gives us the direction of the normal vector. So here we have our normal map, and what we do is we use the red color to denote the X direction, the green color to denote the Y direction, and the blue color to denote the Z direction. Okay, so most normal maps actually look blue because we're looking down the Z direction. Okay, so if you go and build the download and build the project files for this lab, and what you should see is we have our teapots from lab 8. So this was applying our basic lighting models. So here we have direct, a spotlight, and a point light source. Okay, so what we're going to do is apply a normal map to these. A slight change from the previous lab. What we have in this, if I just look at it, in this project we have a light class, and this light class essentially sorts out all of the lighting properties and sends them to the shader. So we have a data structure for each of our light source with position, direction, and color, attenuation values, and cos phi, that was for the spotlight. Okay, so our attributes for each of our light sources, we have methods. So add point light, add spotlight, and add direction light. So that just adds a light source. And if I go to so what we have here is we have a vector called lights, and this will contain all of our light sources. So that's a slight change from the last lab. Okay, so just a bit of a background before we delve into the coding. So when we apply a normal map, we apply all the lighting calculations in what we call the tangent space. Now, if you look at this figure 9.3 here, so here we have a surface. Okay, so the normal vector you should be familiar with by now. This is a vector that points perpendicularly away from our surface, so it's at right angles to our surface. We're going to introduce two extra vectors. Now these are the tangent vector and the bitangent vector. So the tangent and bitangent are perpendicular to the normal, and they're also perpendicular to each other, or orthogonal to each other. So we know we can calculate that, well, the normal vector, that'll come from a normal map. So our normal vector would come from whatever the normal map is, so we need to calculate the tangent and bitangent vectors. Okay, how do we do this? I'm not going to go through this in detail in this video. You could read these materials in your own time. But essentially what we do is we calculate two edge vectors. Now these are the differences in the model space coordinates along edges of a triangle, so edge 1 and edge 2. And we also do similar for the texture coordinates. So corresponding texture coordinates, we calculate delta U and delta V values. So once we've got edge 1 and edge 2 and our delta values, we calculate the tangent and bitangent vectors using this. Again, as I mentioned, there's a more detailed explanation on these lab materials. Once we have the tangent T and bitangent vectors B, we can form what we call a TBN matrix. Now, this TBN matrix, this transforms from tangent space to the model space, or to a different space. Now, we want to go the other way around. We want to go from our view space eventually to our tangent space. So all we have to do is invert or calculate the matrix inverse of this matrix. Now, fortunately, this is what we call an orthogonal matrix. And the inverse of an orthogonal matrix is simply the transpose, which is dead easy to calculate. Okay, right, so to start with, we need to calculate tangent and bitangent vectors, and we're going to do this in our model class. Okay, so if I go to our model class, okay, so here we have our model attributes. Okay, so we got two more attributes. I'm going to call them tangents and bitangents. What I'm just going to do is delete those lighting. We don't need those anymore. Okay, so what this is these are vectors which can contain the bitangents and the tangents and the bitangents, and we're also going to add a private method which essentially calculates those tangents. Okay, so these, you know, can be public, but there's no point. We're not going to call it from outside the class, so I've stuck it in the private. Okay, so then in our model.cpp file, this is our method definition, and I'll just paste this in to the model.cpp. Okay, scroll to the bottom. Here we are. Okay, so if we go just a quick explanation of what we're doing here, so we're going to loop through all of our vertices, and we're going to jump by 3 at a time. Okay, so we're going to take. So each time we go through this for loop, we've actually got 3 vertices. Okay, so first we calculate the edge vectors. Okay, so edge 1 and edge 2, and we also calculate the delta u and delta v's. Okay, if I just go back to the calculations, so now we've got to calculate this. So notice both of these have this common factor here. So 1 over this, it's actually called a determinant. So that's what I've calculated there. And then I calculate the bitangent and tangent vectors. Okay, we need to add them to our list. So because we got 3 vertices of a triangle, we're going to assume they all have the same tangent and bitangent. So we just add 3 tangents to our tangents list and 3 bitangents to our bitangents list. Okay, so that's all done in our model class. Okay, and I've just done all that. Okay, and so once we've done that, what we want to do is calculate the tangents and bitangents as soon as we have a model or a model object. So what I'm going to do here is, this is our constructor for our model class. I'm just going to tell it to calculate the tangent vectors there. Okay, so the last thing we need to change to our model class is we need to send all that information to our shaders, or to our vertex array object. So what I've got to do is just copy and paste this, and this goes in the setup buffers method. So here we have, and so if I paste that in here, okay, you can see we've done similar in the past. So for our vertex buffer, our UV buffer, and our normal buffer, we've done that in the past. Okay, so we've got 2 extra buffers, our tangent and bitangent, and these are essentially the same as what we've done before. So there's nothing different. One thing we should notice is we're using attributes 3 and 4. Okay, so when we do our shader programs, the location 3 is our tangents and the location 4 is our bitangents. Okay. So talking about the shaders, okay, so we're going to need vertex and fragment shaders. Now what I suggest we do here is we actually create a new one. Okay, so I'm going to create a new new vertex shader. So do this in the normal way. If you're in Visual Studio, obviously that's slightly different. And I'm going to call it normal map vertex shader. I'll leave the extension off for now. Okay, so we create that and make sure it's in your source folder. Okay, another thing I need to do here is just make sure that the extension is vert. Yeah. Okay, so at the moment this is empty. I'm going to cheat a little and I'm going to borrow a lot from what we've done before. So I'll take our vertex shader and I'm just going to copy all of that into our new normal map shader. Okay, so this was the standard vertex shader from before. So we had our vertex position, our texture coordinates, and our normal vectors. Well, we need two extra, which is tangent and bitangent vectors. So, and if you remember, we put these in attributes 3 and 4 respectively. Okay, so this means the vertex shader knows what those vectors are. Right. Okay, so I've done this bit. So, and we've got to calculate that TBN matrix. So if I just scroll back up a little bit here, yeah, we're calculating this matrix, and we're also going to be inverting it. So if I go back down, so calculate the TBN matrix. So remember, this is the matrix that goes from the view space to the tangent space. It says model space there. Yeah, it's actually from the model space to the tangent space. So what we're doing here is we're multiplying view by model. Remember, these matrices take us from the model space to the view space. So this actually, strictly speaking, this is view space to tangent space. Okay. And also, so we need to calculate the tangent space fragment position and lighting position and direction. So what I've done, I just undo that there. So this is our previous calculations. So this is all output in view space fragment position and the normal, and output view space light position and direction. So I'm going to change that, paste it in this code. Now this outputs tangent space fragment position and tangent space light position and direction. You'll notice I'm not outputting the normal because the normal will come from that normal map. Okay, so you can see here we have a three element vector. This is our position in the view space, and we're multiplying that by our TBN matrix to give us our fragment position in the tangent space. Similarly with the light position and light direction. Okay, so that's our vertex shader. Now we have to do some changes to our fragment shader. So like before, okay, I'm going to add a new file. Okay, and I'm going to call it normal map fragment shader. Leave the extension for now, and again, make sure it is in the source folder. Okay, and don't forget just to change the extension to .frag. Okay, and like before, I'm just going to take all of the code from our existing fragment shader, because we're actually only making a couple of changes to this. Okay, so the change we're making, we no longer have a normal vector being passed in from the vertex shader, but what we do have is we have this additional normal map here. So this was left over from for some reason from that previous shader. So this is our normal map. So this is just another texture map, and this will give us our normal vectors. Okay, so before we had the normal vectors being passed in from the vertex shader. Well, now we want to assign the normal vector to the normal map. Okay, so what I'm going to do is copy this code in here. Okay, so yeah, so this is just a texture. So here we've got a normal map, and so this is standard, exactly the same as we did for texture mapping. What we've done here is the normal map will have values between 0 and 1. Now, we want our normal vector to have values between -1 and +1. So we scale it. So we multiply our normal map by 2 and subtract 1. So that will scale it so we have values between -1 and +1. The I vector is exactly the same. We don't have to change that. Okay. And that's the only change you need to really make to the fragment shader. Okay, so just make sure I save that. Finally, the last thing we have to do is, this is all our main.cpp file. We have to make sure we're using our new normal map shaders. Okay, so back over to our main.cpp. So if I scroll down where we compile the shader program, what I'm going to do is just comment the existing shader out, and I'm going to replace it with our normal map shader. Okay. We also need to add our normal map to our texture. Okay, so our objects were called teapot. So if I just go back to this, so here we loaded our model teapot, which is OBJ model. See a previous lab. I think that was previous lab 8, maybe lab 7, for one of those. Okay, and we added a texture to our teapot, which was a diffuse texture. Okay, so now we're going to add our normal texture. Okay, so in the objects directory, there's a texture called diamond normal, and the type of texture map is normal. So that's what I'm adding there. Okay, so let's see if that works. So first we try and compile it. Oh, build failed. Remember KA. Yeah. So what I've done here is, if you recall, I deleted KA. So what I'm going to actually do here is enter them in manually. So I'm going to use a value of 0.2 for the ambient. I'm going to use a value of 0.7 for the diffuse, a 0.1 for specular, and 20 for the specular exponent. Now, if you check out Lab 8, you'll see these are just sort of values which we choose to affect how lighting affects the model. Okay, so class member cannot be redeclared. For some reason I've got 2 lots of those in. I must have already pasted them in. Yeah, so okay, that all works. So let's see what we have when we run this code. Okay, now if you're on a Mac, you might find this happening a bit. There's a little bit of a bug in GLFLW which affects the mouse coordinates. So sometimes if you just rerun it, it works. Okay, so here we have our teapots, and you can see the change. We now have this sort of diamond plate pattern or normal map applied to each of our teapots. Now if I move around, you can see it gives the impression that we have this sort of bumpy surface on our teapots. I haven't changed the geometry. Geometry is exactly the same. All we've done is added this this normal map. Now if I do a close-up, you can see it's kind of given the appearance of having this sort of rough pattern. Okay, and it also affects, so as I move around, you can see the specular highlights are affected there. Okay, so that looks pretty good. One thing you may notice, if I just zoom in again, we can see kind of abrupt change in the sort of specular highlights, and we can kind of see where the polygons which make up our teapot join. Okay, so why is this? Okay, so this is something to do with how the blender, which the teapot model was created in, how it exported or calculated the normal vectors. Okay, so if you have a look at this figure here, 9.8, so this is a tetrahedron. Okay, so we've got 4 sides. So here we have this red side here, and now the normal vectors to the red side will be pointing away. So the 3 vertices of this red triangle here will all be pointing in the same direction. Now if you have a look at the blue triangle, okay, again we have 3 vertices all pointing in this direction, and let's say there's a triangle on the back face which you can't see, and it has normals pointing in that direction. Now all 3 of these triangles share this vertex. So in order to save memory, what the 3D modeling software does is it averages those 3 normal vectors to give a single normal vector for that vertex. Now that works fine, apart from when we want to do normal mapping. Now the problem is our normal vector is no longer orthogonal or perpendicular to our tangent and bitangent vectors. Okay, so what we have to do is something called reorthogonalizing the tangent space vectors. That sounds very sort of posh and complicated. It's not really at all. Okay, so what we essentially have is, let's say this is our normal vector. We have a tangent vector which we calculated in the model class, and you can see that this isn't at right angles to our normal vector. So what we do is we subtract our dot product between the tangent and the normal vector, and then multiply it by the normal vector. So if we subtract that vector from t, we have this new t vector, which you can see is orthogonal to our normal vector. Now this is called the Gram-Schmidt process. I'm not going to explain that here. There's a link in these materials which you can look in more detail if you want. Okay, so essentially we need to subtract the dot product between t and n multiplied by n. Remember, n is a normal vector from t. Okay, so what I'm going to do is we're going to do this in the vertex shader. If I go to back to the vertex shader, oh yeah, here we are. So what I'm going to do is I'm going to replace all of this code. So this is the code used to calculate the t, b, and n vectors, and also the TBN matrix, and I'm going to paste in this new code. So what this does is t and n are calculated exactly the same way as before, but then what we do is we subtract the dot product of t and n multiplied by n from t, and that ensures that t is now orthogonal or perpendicular or at right angles to n. Now to calculate the bitangent, we can use a cross product between n and t, so we don't actually have to use or calculate the bitangent in the model class. If you don't want to, you can just calculate it in the vertex shader. Okay, so now we've calculated our t, n, and b, and we know that t, b, and n are now all orthogonal to each other. Okay, so I'm just going to run this code, and let's see what we have. Okay, right, so you can see we got much better. If I sort of move the camera around, you can see we can no longer tell the difference between the polygons on our teapot. Okay, so there was a definite improvement, and it was quite easy thing to do. Okay, so that's re-orthogonalizing our tangent vectors. Okay, the last thing I want to have a look at in this lab is the idea of a specular map. So we just applied a normal map. Okay, so let's say, and what we're going to do here is we're going to apply a floor, and we're going to have a stone floor to our scene. And so our diffuse map is just a texture map of some stones, and we have a normal map which gives us a normal vector. And what we have here is a specular map. Now what this is another texture map. Now where we have dark regions of our specular map, that's going to affect the amount of specular highlights. So remember the specular constant, the Ks. Well, this is essentially the Ks. So where we have light areas, we've got a high specular value for Ks, and where we have dark sections of our specular map, we got a low. Okay, so that will control where we're applying specular reflection. Okay, so what we're going to do is we're going to add some more objects to our scene, and because we'll probably want to, likely we want to do this, a scene has more than just one teapot. Okay, what I'm going to do is I'm going to use a data structure. So in our CPP file, okay, I'm going to introduce a data structure just before the main. Okay, now this data structure is going to contain all the information for a single object. So each object in our scene is going to have a position. It's may have a rotation vector, and we may want to resize it. But so for default, the position is at 0, 0, 0. The rotation vector is just a vector pointing straight up. Scaling is default is going to be 1, 1, 1. So by default we're not changing the size of our object. And angle, this is the rotation angle, so it's a 0. And I've got those Ka, Kd, Ks, and Ns default values here. And we also got a name, which is a string for our object. Okay, so what I want to do is we're going to have two main objects in addition to our light source object. So I'm going to replace where I've loaded these models here with that code pasted from the notes. Okay, so we're going to have our standard teapot object. We have our light model object from before, and I've also got another type of object called floor. And in the objects folder of this project, there's a flatplane.obj, and this is just it's simply a horizontal flat plane. Add the diffuse and normal textures to our teapot, and I've added diffuse and normal textures to our stone floor. Okay, and what we've also got to do is define the objects and put them in a vector. Okay, so this code here, if I paste this in, okay, so I'm no longer going to have 10 teapots, so I'm just going to have 1. So I'm going to just delete that code. And what we have here is I've defined a vector of objects, and I've called them objects, a sensible name. And here I've defined, I created an object, and this first object name is teapot, and I add it to our vector. So that teapot is just going to have the default. It's not going to be scaled. It's just going to be at 0, 0, 0. The next object I have is floor. So changing the object name to floor, and I've moved the floor down a bit so it appears underneath our teapot. So you can see I've moved it down by 0.85 in the Y direction. And again, I've added it to our objects vector. So our object vector contains 2 objects. And I could add more if I wanted to. I could have more teapots or more other type of objects as well. Okay, so now what I need to do is draw those objects. So where I did that before, so in place of this for loop, I'm going to paste in the one from the lab materials. You can see it's very similar. So objects.size, that's quite a handy command, because that gives us how many objects I have or I want to draw, so it loops through them all. Calculate the translate, scale and rotate matrix. So for each if object we take its position, scale and angle, and that will give us our model matrix. Okay, the lighting constants, so again that comes from our if object, and where we draw the model. Okay, so here we have a teapot model. So if the name is teapot, we call the draw method for the teapot object, and if it's floor, we do similar for floor. So if you have a different type of object and you give it a different name, you'd have to add another if statement to be able to draw that object. Okay, so I'm just going to see if this compiles. It does, and I'm going to run it, and let's see what we get. Okay, again there we go. So here we can see we now have our floor. So you can see the floor is beneath our teapot, and you'll notice as I'm moving around, the lighting calculations for the floor applies. Okay, so it looks good. But one thing you may notice, and if I just sort of try and point it, okay, at an area, okay, you may notice that we have some specular highlights at this sort of where each of these stones, the join of each of these stones, and there should really be mortar, and mortar's sort of rough, and we shouldn't really be seeing sort of specular highlights between our stones. So what I'm going to do now is add a specular map to this scene. Okay, so specular map. So all I need to do is add a texture. Now in the objects folder, I've already got a specular map contained in there. Where did I add the here? So I'm going to add a specular map to our floor object. Okay, and we also need to make some changes to the fragment shader. Okay, so in the fragment shader I have a new texture map. So if I go back to my fragment shader, so we now got a specular map. By the way, if you're wondering how does this get passed through to the fragment shader, if I go to the model, class, you can see in where I've got the draw method, this adds the each of the texture. So I've got a texture type, so we've now got an additional specular map, so that sends it to the fragment shader. So this is that's done automatically by that model class. Okay, so we have a specular map. Okay, now what we're going to be doing is wherever we calculate the specular lighting, we're going to multiply it by our specular map, and that's all we do. It's quite a simple calculation. This specular map gives us a textile with, where I said if it's a light color, this will increase this calculation. If the specular map has a dark color, it will decrease this calculation. Okay, so wherever I've got this specular calculation, okay, so what I mean is this one here. Okay, I'm just going to replace it by pasting in. Okay, and that's for the point light source. We've also got the similar for the spotlight, and we've also got similar for our directional light. Okay, so let's run see what this does now. Aha, yeah. So you can see it looks fairly similar, but if we then take a closer look between our stones, you can see that where the specular map is darker, you can see but no specular reflection occurs, and it looks much more realistic. Okay, so that's normal mapping and specular map.